Brilliant, thanks Gordon. And first of all, can I just check that everybody can see that? I seem to have done something with my double screen. Excellent.
Yep.
Thank you. And yep, I've noted I am handing over to Chris Dent after myself. Okay, so thank you, Gordon. And what I wanted to do was just take you through some work that we've been doing at Heriot-Watt, looking at urban systems modelling. It's not just myself. I'd like to introduce the team who are also on this slide. Very much a collaborative effort. Mention Melissa, David and Gordon, who are all on the call today as well. It's funded under EPSRC, and we've done it as part of the Water Resilient Cities project. And really what I wanted to do was introduce that we've started talking very much about systems and interconnections and interdependencies, and that's what we try to do with this model, and that's what I'll try and introduce today and talk about how we see that we could usefully work in the future with DAFNI. So it's termed a systems approach for hazard and resilience. Right, so recognizing that cities are tightly coupled systems, what we wanted to do was to build a model that recognized the interconnections. I think something that COVID-19 has really exposed to us is how interconnected our urban systems are, how interdependent they are whenever we have a shock. So the impacts of hazards can be both short-term and long-term, but these hazards cascade through our sectors and cause devastating impact within our urban systems. And what we wanted to do was understand both the short-term emergency response, but also how these hazards trickle up through the system to impact on our longer term, higher level outcomes. And that's often where we track resilience. So resilience in the city, in the system or in a city. So we built a model, it's a network model, and it's based on an abstraction hierarchy. So the hierarchy is built into the system. That means there's levels in which we interconnect, and it's effectively a network. So we have 5 levels within our abstraction hierarchy, and at the bottom you start with your very tangible physical objects, and as you go up through the hierarchy you can connect based on functionality. So as you move up through the hierarchy you're getting increasingly intangible within the system. But what it does do is allows us to understand how we can map how our physical objects, for example, a bus station, might impact economic opportunity right at the top of the system. So this, an abstraction hierarchy is a developed method, but it tends to be done on a very small scale. And what we've done is upscaled this and adapted it in order to model urban systems and then make them specific for particular cities. So what's important is each level in this hierarchy is connected through functionality. And what we have done is built into this system at the values and priority measures level up here and the blue level, and the resilience indicators such as 100 resilient cities. Now you could also use indicators like the Sustainable Development Goals, but the more intangible long-term resilience goals that we often use to measure how well a system is operating. So if you start at the bottom of the system, you can ask yourself, you have the physical objects at the bottom which afford your object-related processes that happen, up to the generalized functions, and then the values and priority measures and the functional purpose of the reason a system exists at the top. So moving up through the system, you can ask yourself why something exists, or moving back down, you can ask how. So if we take, for example, bus stations at the bottom, you can see that that's connected to generate traffic information. In our data-hungry society, all of the bus stations are creating real-time data on traffic information. Those processes allow us to understand better about our road conditions and safety in the real time. And that in turn allows us to understand reliable communications and mobility, so we can avoid traffic jams, therefore allowing functional purposes at the top of economic opportunity. becomes much more abstract the further you go up, but it allows us to make this systems map. It has 5 layers, as I've mentioned before, and we have around 480 nodes, and that's connected using over 4,500 links. So it's really complex, but the idea is that it allows you to map the interdependencies through different sectors within this map. In order to navigate the system, you need to use network metrics. Now, there are lots and lots of different metrics that you can use. The one that we currently use at the moment is eigenvector centrality. It allows us to look at the most influential nodes within a network based on the importance of a particular node's neighbours. So it allows us to look at how important that chain is from the bottom to the top or from the top to the bottom in relation to other nodes within that level. In order to do that, because when we started it was very small, and where we see the potential links with DAFNI here is that we've developed 2 pieces of code. I've included the GitHub references there if anybody ever wants, and I'm aware that these will go out in future. So the first one is, if you saw at the bottom of these networks, they all require the physical object. So the first thing that we needed to do was build ourselves a piece of software that allowed us to collect all the information within a city region, count it, and allow us to have enough information about all of the different physical objects within the city to put into our network model. And that is completed using a piece of software called OSM Tidy, where we take the OpenStreetMaps, we cut out the bits that we're interested in, we wrangle, filter and count the data and tidy it into the format that we need into the next component, into the next section. We then have created another piece of software called AHGen, which generates the city model itself. We take the input from OSM Tidy, we match it up, we filter out objects that don't exist within a particular city, for example, and then we create our city-specific model. Again, there's the GitHub reference if you were interested. Currently, we've created 6 models within the UK, so 6 city models, and that includes Belfast, Bristol, Edinburgh, Glasgow, London and Manchester. For those of you included in UCRIC, it's 4 of them are within the core cities section, and 2 of them we've included Edinburgh because that's where we're based, but also London. I'm putting in there a kind of indication of how long these models take to create. We're looking at a normal city of about 1.5 weeks to develop a model, 1.5 to 2 weeks to develop the model, whereas London being a bit bigger and more complex, it took us a bit longer. Just to give you an idea. But once you've created this model, we can then adjust for the hazard at the bottom. So when I say adjust for a hazard, that could be anything from floods or droughts through to the pandemic, and I'll explain that we've modelled both in a minute. But what it allows you to do in a different way than in a spatial manner, what it allows you to do is to take a particular node. Again, if we look at the bus stations here, we can introduce that hazard in that layer. So we can take that node and we can say, okay, it was flooded, so we have to knock out all functionality of that node. So all of these different processes that node affords in a flood would be knocked out. So we can knock that out, rerun our network metrics and understand what the impact is over the short term and over the longer term. If, for example, you wanted to model a cyber attack, you might just pick up on this, the impact of generate traffic information. So suddenly bus stations can't generate that traffic information. So what would that do to the network? So we can then have a look at what that might do to our longer term intangible outcomes. There are 3,550 potential edges or links in that bottom layer. So from the physical objects to the processes that you can then, to use a better word, play with to understand the impact that they may have on the longer term intangible goals. And you can track that hazard scenario using the eigenvector centrality or different network metrics, depending on what is best for understanding the network. So currently we have, because we come from the water environment, we've developed two different hazard scenarios with this model. One is looking at flood hazard, weighting the node and knocking out a node. That allows you to reflect flood exposure and take out the node's functionality. And 20% or so of potential edges in that bottom layer were knocked out when we modelled a flood event and we tracked intangible exposure. Conversely, looking at COVID-19 and when we modelled Edinburgh with the Scottish Government, what we did was we impacted different edges and the links between the physical objects and the processes to reflect what lockdown looked like. And therefore 56% of these edges were modified or in some way changed functionality to reflect this capacity. And then we could track the change in the exposure further up in the network. So I won't go into the results, but I'm more than happy to talk to other people whenever about this. But what I wanted to do was say that we've developed this model. This is, and it's available for 6 UK cities, and we can track different hazards. But where we see the potential, particularly within the team, is working with DAFNI to house the models, to improve the availability of these models if anyone's interested in using them. Potentially going forward, looking at upgrading the analysis metrics, looking at how we might do more complex numerical coding, and develop better visualizations. So I'll stop there and I'm going to hand over to Chris Dent, who's now going to talk about a different project coming from Edinburgh University.